Welcome back. Last time we talked about Burke's theorem. Today I want to move to another topic. Basically, I would say a topic is beyond queuing. We want to look into a system with lateral queues instead of like just one queue. So before doing that, let me just review the MM1 queue, the simplest queuing system first. Basically, MM1 is just the first M stands for the arriving process is Poisson, and the second M is just saying that the service time is exponentially distributed, and also the service times supposed to be independent of the arrival time. And let's think of like when this model and this kind of modeling assumption will hold. For example, think of a network used to transfer packets from one end to another end. And we have packets going into this system supposed to be Poisson. It's just saying that the packet arrive at time that is kind of independent of like previous arrival, and also the arriving rate is kind of constant. So therefore this is not exactly a very strong assumption. It's kind of reasonable in some sense. But for the second M, basically it's saying that the service time should be exponential, and one rationale for that can be like each packet have different length, and basically the service time is proportional to length of the packet, and also like the distribution of the length is exponentially distributed. So I would think that this is actually a stronger assumption than the first assumption that the arrival statistic is Poisson, but it is still like a reasonable assumption in some cases. So, but let's say we even have this kind of assumption that, okay, the arrival statistic is Poisson, and also the packets are distributed with length exponentially distributed. But even that, let's say now instead of having one queue, let's say the packet going through this server, and after it's being processed, this packet fit into another queuing system, and again, like the service time will be just proportional to the length of the packet. So of course, like the first queue will be MM1. It doesn't affect the fact that like whether it should be MM1 or not if we cascade something afterward. But the problem is like the second queuing system here, second queue here, will no longer be MM1, because first of all, the first M is actually okay, because like from the Burke's theorem we discussed last time, the departure statistics indeed will be Poisson with like the weight will be lambda, simply because like the MM1 is like a reversible system, time reversible system. It means that like the time reverse system will have the same statistics as the original system, and of course in the time reverse system, the arrival time is actually the departure time of the original system. Therefore, the original system, the departure time, the departure statistics will also be Poisson and with rate lambda. So the first M is okay, but the problem is the second M, because if we think of that, the packets will still have length being exponentially distributed, but the problem is that it is no longer independent of the arriving statistics. For example, let's say just have an example like this. We have like a couple packets like getting through the first server. Let's say this is a time axis. This represents like there's a packet that arrive at this time and being served for so long, and then this is a departure here, like at this time, and then there's another packet starting to be served at this time, and this is a rather long packet, take a long time, and then it depart here, and another packet and it depart here. And now if we think of that, the interarrival time between the departure of this very long packet and the departure of the packet before this very long packet is very long, and we expect that therefore when the departure time is very long, there's a chance that actually a probability, rather correlated probability, high probability that it probably is due to the fact that the packet is simply, the packet that is being served at the moment is very long. So therefore, when the arrival time, interarrival time is long, we can kind of predict that the service time will be long also. And this exactly violates the independence between the arrival statistics of the departure and the departure statistics of the MM1Q. So therefore, even we have the assumption that arriving statistics is Poisson, and length of packets are exponentially distributed, and therefore will be processed with exponentially distributed time. Still, if we cascade several of these server together, we cannot model all these server with MM1Q with, I would say, perfect accuracy. I mean, it cannot model the system with 100% accuracy. However, that's probably because MM1Q is basically the simplest queuing system. Sometimes we may want to just assume that it's MM1 anyway, and see how's the simulation results go and so forth. And actually, there's have a name for this kind of assumption, and it's introduced by Kyrok. And when you have a network of queues, and we assume all these queues are just MM1 queuing system, this very simple assumption is also known as the Kyrok independent assumption.